All right, so we're going to look at the average function some more. And so here is kind of the thing we were discussing, where here we've got an int function or an int output, and here we've got a float output. So we've got float average and we've got int average, and they are doing essentially the same thing. Now, because this has an input of ints and this has an input of floats, this should work okay, because it's not really the output type that's calling the shots here. It's the inputs, the parameters that are actually creating distinct signatures. So if we run this, it's giving us the average, which is 22. It's doing this one because these are integers. So it's finding the one that applies to integers and not floats. Because technically the answer is 22.5. Now, if on the other hand, I were to do this, for instance, 10.0 and 35.0, if I wrote them as floats, so now we're actually running into an ambiguous case here, because we basically got like an identity crisis. Are these supposed to be integers or are they supposed to be floats? So here we have the same function. It averages 2 floats and the other averages 2 ints. They each return something that matches what the input is. If we call it with 2 integers, it'll match it to the 2 integers. So we don't have to convert. If we call with integers, it gives us the integer answer. So you saw, though, that it was problematic, because you can even see here that call of overloaded average double is ambiguous, because technically these numbers that I've given it are both integers and floats, and that's what's causing it problems. Usually you don't want to have the difference just be the variable types. Usually you want to have a more substantial difference in what the function actually does if you're doing something like this. Let's see. So variable types, we've seen several different ones here. You've got like ints, floats, bools, chars. We've talked about voids, which is a special one for functions where it doesn't actually return anything. And then there's also string, but you do have to include the string library in order to get access to strings. So fun fact, there are actually different variable types, like subclasses, if you will. And this actually has to do with how much space they will take up in the computer's memory. So you could have one that only goes up to 8 bits and the other that goes up to 16 bits. And in C++, you can specify sort of how many bits you're going to reserve for storing numbers. If you have more bits, you can hold more amounts of data. So with floating point decimals, you could have like more precise measures with lots and lots of more decimal places. So an 8-bit integer is able to represent 256 different numbers. The reason being 256 is 2 to the 8th power. These are in binary, so they're all zeros and ones. It's all base 2. And if you have 8 digits, it's basically just 2 to the 8th power, which is where this comes from, 256. 2 to the 32nd, I don't happen to know off the top of my head what number that is, but it's going to get you a number close to 4 billion. So if you have 4 times as much space, you can drastically increase how much, how large or how precise your numbers can get. Kind of. I'm coming up to that like right now, actually. That's like literally the next thing. So you can kind of do this because there are subtypes of variables. So we have seen ints up to now. There are actually other ones. There's actually a type called short int, long int, and then there's also long int. And then like for floats, you've got float double and long double. And so each of those, in that order, they get progressively larger because they allow larger amounts of memory to store values. So like long int, I think long int is like a 32-bit one. Long int is, I want to say 16. Int is 8. And then actually short int goes up to only 4 bits. So like little bitty numbers, you can really save on how much memory you need if you use short int. A lot of the time, you don't have to worry about this because C++ is designed sort of in the background to, like, if you declare an int, but then give it like a humongous number, like a 9-digit number in the billions, it'll like automatically make it like a long int, even though you didn't specifically tell it to. No, because this kind of, I mean, unless you're talking about strings, which do have their own libraries, these are all like components of vanilla C++ that are not really dependent on any actual libraries. So greater usage of memory, it can increase the precision, but it's also going to seriously slow down performance. And things that slow down performance also like compound themselves over time. And so, you know, a loss of a couple of nanoseconds here and there may not be a big deal, but if you stack that, like if you're talking about stuff with graphics in a huge game engine, a lag of a few nanoseconds that like cascades can really, really make a huge difference. And so sometimes it's like, bro, you need to do the 32-bit graphics because you so don't have the 64-bit graphics card that can actually handle this. Like quit trying. It's more hassle than, you don't have to have absolutely perfect resolution. Anyway, so what do we got? So for functions, the compiler might have to convert variable types to match the signature of functions. So why we're bringing this up now is that you may define a function for an int, but it may have to convert it to a slightly different kind of int based on the size of values you're passing to it. And anytime the computer has to do something like convert from one to another, that's going to slow it down. So fun fact, from the computer's perspective, int and long int are actually completely different. So it's got to go through the process of converting them, because in the computer's mind, those are different, even though to us, we're like, bruh, they're just numbers. But so what we got? So I actually had code that already did this, and I just changed the old program and did the exact same thing anyway. But there you go. So we've actually already seen that. So we're calling the function with floats. You might expect it to convert them, but what in fact happens is you get a compiler error, and it can't decide if it should make those into ints or floats. Because these are point zeros, it's having to convert them because I think short int only goes up to like 32, which is why 35, it has to convert to a different variable type. So it's having to make a conversion from like a short int to like a long int or something like that. Whereas it could also be converting to a float. And so that's why you have this ambiguous declaration that's making it grumpy here. One way to avoid this is if you put F on the end of a number, it will convert it to a float automatically. So here is the workaround. So for instance, here we've got 10.0 F, 35.0 F. And what the F is doing is it's telling the compiler, hey, bruh, make this a float. And it's like, right on, bruh. And then it knows which function to go look at based on the signature. And it's like, oh, it's 22.5. And you're like, sweet, bruh. And the function's like, no problem, bruh. So what do we got? So in a similar fashion, you can attach LL, and that'll make it a long int. And there's other like abbreviations too you can use. But if you overload a function, the types need to be passed specifically to match a given signature. Otherwise, it's going to get grumpy at you, basically. So beware of overloading functions. It can cause headaches.